All right. Thank you very much for the invitation. Let me try to see if I know how this works. OK, I do. Good. So I will talk about work that I've been doing this past year with Shai Chester, Sheehan, Damon Binder, and so I mentioned work in progress with Damon Binder, Shai Chester, and Yifan Wang. So there are two dreams of ADS-CFT. One of them is to learn about the bulk from the boundary, learn about quantum gravity or string theory or M theory from the CFT, and the other one is to go the other way around, to learn about QFTs, strongly interacting quantum field theories from the bulk. And in this talk, I'll try a little bit of both. Although the new results will be only for learning about the quantum field theory from the bulk. The examples of ADS-CFT that I'll focus on are these two, perhaps the more well-established ones. The duality between 4D n equal 4 super Yang-Mills theory with gauge group SUN at large n and large 2th coupling. Is dual to type 2B string theory on ADS5 times S5. And the other example is between 3D UN times UN ABJM theory. So the ABJM theory has two gauge groups. Both of them are UN. And there are Chern-Simons interactions K and minus K for the two gauge groups. And at fixed K and at large n, this is dual to M theory on ADS4 times S7 mod ZK. In this talk, for simplicity, I'll just focus on the case k equal 1, where this is just ADS4 times S7. Both examples have maximal supersymmetry. And actually, that's part of the reason why what I'm going to say works. OK. So the goal, I guess this thing is just cut it's cut off from the connection between three topics. The three topics are 4-point scattering amplitudes in 10 dimensions and 11 dimensions. They're scattering amplitudes of gravitons and their superpartners in the 11D case. In the 10D case, it's the same, or you could also think about them as the massless closed string states. The second topic is conformal field theory of 4-point functions with their various properties, crossing, symmetry, word identities, analytical and numerical bootstrap. And the third topic is exact results from supersymmetric localization. The connection between the first two topics is not new. There was a conjecture, well, also maybe proven relation between CFT 4-point function and scattering amplitudes. Sorry, CFT correlation function and scattering amplitudes. I guess what I'm trying to bring in is supersymmetric localization.
The scattering is in flat space?
The scattering is in flat space, yeah. The idea is that we can relate CFT correlation functions to scattering in ADS, and then we can take the flat space limit and get scattering in flat space. OK. So in particular, what will I do? Using the last two, CFT 4-point functions and the results from supersymmetric localization, I will aim to reconstruct part of the string theory or M theory S matrix perturbatively at small momentum. And I'll explain to what extent one can do this. Equivalently, one can think about scattering amplitudes, or one can think about the effective action. The effective action in either 10 dimensions or 11 dimensions starts with the Einstein-Hilbert term plus its supersymmetric completion, and then there are higher derivative corrections. The first higher derivative correction is Riemann to the 4th interaction, and then there's plus its supersymmetric completion, and then so on. So that's one thing that one can do, and the other thing is to use 1 and 3. So use information about the scattering amplitudes and also use what we know about from supersymmetric localization to get more information that we knew before about the CFT 4-point functions. So I'll explain both. So I guess the first one is like, learning about gravity from the CFT, and the second one would be learning about the CFT from the ball. Okay, so in 11D, what can we scatter? Well, we can scatter the particles that we have, which are gravitons and their superpartners, gravitini and free-form gauge particles. I'm only going to be talking about 4 particles. For 4 particles, we can restrict the momenta to lie within a 4-dimensional subspace without loss of generality. And because the momenta are within 4 dimensions, we can use 4D n = 8 supersymmetry language in order to describe the kinds of particles that we're scattering. We have the graviton, we have gravitinos, graviphotons, graviphotinos, and a bunch of scalars. So for instance, if we start with an 11D graviton that it's polarized in the directions perpendicular to this 4D subspace, then those would be scalars from the 4-dimensional point of view.
So maybe you're missing something
Yeah.
small, but one could make it lie in a 3D subspace, right?
Sorry?
One could even lie a scattering process would make it lie in a 3D subspace.
Don't you have 3 independent movements?
Yeah, you have 3 independent. So there's time, and then there's space. So I can have the momentum of the first, they're massless particles. So,
I think he's right. There's a plane, a scattering plane with space and there's time.
it is a, yeah, right.
Yeah, but in particular.
In particular, for
Sorry, then I'm embarrassed. I thought you had 4 particles, you have momentum conservation, so you have 3 independent momenta.
that's also,
Which is 3D.
yeah, and
that's
plus,
why
then
4D
plus time is 4.
Is including 4.
4 independent space-time momenta. In space-time, there's 3 directions.
I guess that makes sense. I guess it makes sense. Yes.
All right, fine, I'm sorry. I was
Imp-
being a
imp-
Newtonian physicist. Okay, yeah, it's true, I'm sorry.
Right. Well, in the next slide, well, okay. The statement is correct. Okay, so what do these scattering amplitudes look like? Well, at leading order in small momentum, leading order meaning momentum squared, we have scattering amplitudes in n = 8 supergravity at tree level in 4 dimensions. So, tree level scattering in 11D is the same as tree level scattering in 4D. For instance, if we take, the scattering amplitudes depend on the type of particle that we're scattering. For example, if we have 2 scalars of one type and 2 scalars of some other type, I didn't say what type it is, then we can get formulas like this. So there's just some function of the Mandelstam invariance.
This plus STU flips.
If we look at other particles. For this particular one, 2 scalars of this type and 2 scalars of that type, I think. Well, I didn't tell you what scalars these are.
Okay. This is something that only 1 with 2 can go to. Oh,
But that's right. Yeah. Anyway, so the amplitudes depend on the particles being scattered, but they're all related by supersymmetry. So one can figure out what they are. It's not going to be important.
This book.
That's a book on scattering amplitudes, and they have a formula. Right, that's written in the spinor helicity formalism. That a very compact formula for all the supergravity scattering amplitude of all these particles.
So once the scattering amplitude of the conformal, the supersymmetric primal is given, the scattering amplitude of any 4 particles in that multiplet is fixed.
Correct. Right. Okay, so this is at leading order in momentum. What happens at high orders in momentum? Well, the expansion takes a universal form up to an overall prefactor, which is the supergravity tree level scattering. It's at, the expansion in momentum, in small momentum is this, so supergravity tree level scattering times a function of S and T. And that function of S and T can be expanded in well, L Planck times L Planck squared times S and L Planck squared times T. So at each order, I can think about expanding in momentum, or I can think about expanding in L Planck, bidimensional analysis. At each order in the expansion, these functions are homogeneous of degree, whatever the power of L Planck is, divided by 2. Some of them are polynomials in S and T, and some of them are more complicated. The ones that are polynomials correspond to tree-level interaction vertices. So,
Again, the high derivative predictions, the scale for that is set by L Planck.
yeah, that's the only parameter.
Universality is a consequence of n equals 8 supersymmetry.
Yeah, it's a consequence of supersymmetry. Yeah, that's right. Sorry?
Maximal supersymmetry.
Maximal supersymmetry. Okay. So in particular, the f's that I denoted by d to the 2n r to the 4th are symmetric polynomials in STU of degree n plus 3 because they multiply, well, they come multiplying L Planck to the power 2 times n plus 3. The first few are known from string theory calculations, lifting string theory scattering amplitudes. The r to the 4th one is known, it takes this form, and d to the 6th r to the 4th, that's the next one, is known, and it looks like that. Supersymmetry in 11D allows a d to the 4 r to the 4 term in this expansion, but it is known to not be there. Yes?
So even though the Einstein term
Yeah.
is like not symmetric in ST and U, but the corrections are all symmetric in ST and U.
Yeah, but I mean, it's whatever multiplies this thing. So the corrections are also not going to be symmetric in STU, but they're not going to be symmetric in the same way as the Einstein-Hilbert term.
So the correction factors are all symmetric.
Yes, that's right, that's right.
So why?
It's a consequence of supersymmetry.
So you said some of these are polynomial and some are not.
Yes.
Presumably the only non-polynomial ones are those that come from 3.3 level exchange.
From
Yeah,
loops, from loops. From tree level, we're still going to get polynomials.
Okay.
Right. But from loops, we won't.
I see. So now the tree level exchange, that ends at some point, right? Meaning at some order. The highest tree level exchange is like the highest 3-point function is 6 derivative. Right? It's like an R cube term. At least if I'm thinking of gravitons.
Yes.
So if I make a 4-point out of that, that's like 6 times 6.
But that's only if you consider the Einstein-Hilbert action, maybe?
No.
No.
Just 3 graviton scattering has only 3 possible structures. So the highest structure of that is 6 derivative.
Okay.
So 6 plus 6 divided by 2 for the propagator. So 10 derivative is the highest 4-point function you can get out of tree level exchange, I would have thought. But of course you can keep getting loops. Sorry, it's not a very important point. I just wanted to check it.
But well, I haven't thought about that. But can't you have like interaction vertices though? Like not exchange diagram, contact diagrams.
But those would be, I mean, the classical parts of those would all be polynomial.
That's right.
Yeah, of course, that you can just go on.
Okay. Good. Anyway, I'm only going to be talking about the first few. So
Yeah.
Yeah.
To the 10,
yeah.
because Shiraz's counting just had 10 derivatives, right, for the exchange guy. Is that saying something about the 3-point, some constraint on the 3-point vertices? Or the exchange diagrams?
That I'm not sure. You're asking related to this comment that this one vanishes? This is known to vanish because there's no string theory amplitude that can lift to it. It doesn't have the right dependence on G string.
So even more basic question before looking at the scattering. If you look at just 3-point,
Yes.
then what sort of vertices does the string theory give?
if you look at 3-point scattering. Okay.
Sorry, what was the question? You look at 3-point, that will give you some of the allowed.
Either R square or R cube. There are three structures.
There's a 2-derivative term, a 4-derivative term, and a 6-derivative.
Yes. Yes.
And which of them
Which
do you get?
some of these happen to be zero.
to be vanishing? Okay.
I don't know which ones vanish, which ones don't. We can look into it. Yeah. Okay. This is 11.
Really sorry,
Yes.
you must know, just to understand, you can't do field redefinitions obviously in one structure to another, right? So this is.
And when you write the amplitude there, you're looking at the scalars, external scalars.
It doesn't matter what you're looking at.
But if you have indices, then maybe you mentioned this, but how are the polarization vectors being taken care of?
The polarization vectors will appear here, and they will also appear here.
The supersymmetric gives you a particular structure.
Yeah. Yeah. So in this case, I give you an example of scalar scattering, but I could have also written down some scattering of particles with spin, any of the other ones. And then it's more complicated because the polarizations that will appear on the right-hand side.
Polarization can be pulled out like that.
But the point is, yeah, the point is that here the polarizations can just be pulled out, and they have it's the same dependence. The general amplitude has the same dependence as the tree-level scattering, tree-level supergravity.
It's basically your statement that the primary scattering determines all the others.
Right.
The polarizations are all the others, right?
Right. Okay, so that's 11D. 10D, we can scatter. It's the same idea. In 10D, we can scatter gravitons and their superpartners. In this case, I'll take the momentum to light within 5 dimensions. Because of that, we can use 5D n=8 language. In 5D n=8 language, okay, it's the same story as before. We can scatter gravitons, gravitinos, and so on, up to scalars. In this case, there are 42 scalars. And now the scattering amplitudes have an expansion, and there's 2 parameters. There's a string length and the string coupling. So there's an expansion both the string length and the string coupling. And it takes a similar form is the tree-level supergravity one times then a function of S and T that's expanded both in LS and GS. The leading term here that has the smallest power of GS, in this parenthesis GS to the 0, is completely known. It's in Polchinski. It's a ratio of gamma functions. We could take that ratio of gamma functions and expand it in LS if we wanted, and it will look like that, and the coefficient will be polynomials in S and T. These terms over here are more complicated, and I'm not going to talk about them. You know, because the whole thing is known, we can read off what these coefficients, what these functions of ST and U are, and these are the first few. R to the 4th, then there's D to the 4R to the 4, and then D to the 6R to the 4, and so on. So in this case, D to the 4R to the 4 appears.
But here we can answer Abhijit's question, because we know that in string theory there's no R cube correction. Right? The first correction starts at R to the 4. Right?
Correct, yes.
So the 3-point function is just answer.
Sorry, but the same is true in 11D.
Good. So
Good, yeah.
That's where explains a lot of absence of constructions.
Yeah. There's no R cube
Yes.
because of supersymmetry.
Right.
Yes.
Right.
Sorry, I didn't read.
Yeah.
Got here late. Okay, so in this talk, what can we show? We can reproduce FR to the 4th and show that FD to the 4R to the 4th is 0 in 11 dimensions from ABJM theory. And in 10D, can reproduce FR to the 4th from n=4 super Yang Mills. Okay. And the other thing that I'll show you is to use the known facts about scattering amplitudes and the other things that I'll tell you to learn more about the CFT. So in particular, from 11D, can use the next thing that we cannot determine, namely FD to the 6R to the 4th, that's known. And then the other things that I'll explain to determine the first few terms in the 1 over n expansion of the stress tensor multiplet 4-point function. And I'll show you exactly how far one can go. And in 10D, we can use the next one that we can determine, namely fd to the 4r to the 4th, to learn more about the CFT 4-point function. And in particular, what we'll be able to compute is the following. So in n equal 4 super Yang mills, in the stress tensor multiplet, there's a superconformal primary that transforms into 20 prime representation of the SO6R symmetry. We can consider this 4-point function of this 20 prime operator. And we can expand it in 1 over n and in 1 over lambda. What I'm going to be reproducing is the leading term in the 1 over n expansion and the first few terms. So in the leading term in the 1 over n expansion, that can be expanded in 1 over lambda, and I'll be able to determine the first 3 terms in that expansion, in the 1 over lambda expansion. So those will go like 1 over lambda to the 3 halves, and 1 over lambda to the 5 halves. And I'll be able to generalize this computation from not just the 4-point function of the superconformal primary of the stress tensor multiplet. There's a tower of other half BPS multiplets that are labeled by some integer p that starts at 2. And I'll also be able to do the same thing for O2, O2, OP, OP.
You come to this, but let me ask you just a
Yes.
structural question. Particular terms in the bulk determine data for some double trace exchange on the boundary, right? In the 4-point function.
Sorry, you say again? Yes.
If you take a particular contact term in the bulk,
Yes.
and you ask what that translates to in terms of the OP on the boundary,
Yes.
it impacts some double trace exchange on the boundary.
Yes.
And so you would naively think that it tells you something about the exchange of some low spin double trace exchange, and,
Yes.
and nothing more. Is that the same thing as what you're saying? Are those different coefficients, for instance, parameterizing the spin of the exchange of the double trace?
These coefficients.
I can ask you later.
I need to think about it.
But do you know what I mean about the double trace?
I think you're right. I think these things just contribute. Yeah, I think they will contribute only to the anomalous dimensions of the of operators with spin up to some value.
Right.
Yeah, I think that's correct.
And I was wondering whether there was some connection between that spin and this lambda expansion. Right.
Well, yes, there is. The spin grows with the order in the 1 over lambda expansion.
Okay.
And sorry, behind the curve, but just to understand that question, I mean, the double trace involve 2 stress tensors or the SUSY derivative.
Yes.
Connected pieces, right? And the spins will then be of that multiplet or whatever.
Yeah.
Whatever involves the
And,
stress.
there's this simple rule that if you take 4-point function and you cut it,
Yeah.
then the number of indices exchanged in that cut gives you the spin of the double trace exchanged. So since he's got only a few
Yeah.
number of derivatives, there can't be too many.
Right.
So in 11 dimensions, if you look at the scattering amplitude, the exchange piece of the scattering amplitude.
Yes.
Coming to the exchange diagram, what is known about it up here? Spectrum of particles.
The exchange of
So the
Yes.
S matrix, there are
Yeah.
look at 3-level S matrix, let's say, not even loops.
Yeah.
These contact diagrams are the exchange.
yes.
So if you just look at the exchange piece, what is known about it?
The
Apart from the graviton exchange.
the formulas that I wrote before include both the 3-level and exchange.
And you can't separate anything that's not supergravity. You can't separate those counter terms from the loops. There's no parameter separate.
Loops. Okay.
You see,
But probably analyticity would.
At low orders in the expansions, you can separate them,
Okay.
but at higher orders, no. Right. So
The loops with the local contact terms, those you can from the analysis.
Yeah, but you know, I think Abhijit is asking the question, what are the poles in the S matrix, right? I think the only I don't think there's any answer to that other than, I mean, please correct me, but other than just supergravity.
What about the massive particles in the spectrum?
The limit at which you take the supergravity amplitude, they're not there, and the limit at which you go away from that, they will decay.
Decay meaning, sorry?
There's no string coupling here.
Yeah.
So every massive particle is unstable. There's no stable massive
Oh,
particle.
sorry.
Right.
Yeah.
It's not like string theory. We can take
Yeah, I
string
started
coupling
off
to zero.
saying the tree level, but there's no.
There's
Yeah.
zero limit.
Right. Okay, and another comment that I wanted to make was, from this 2 pp 4-point function, one can put two of them together and figure out order 1 over n to the 4th corrections to various pieces of CFD data. I won't say much about that though. Okay, the idea is that flat space scattering amplitudes can be obtained as limits of CFT correlators. So for example, if we have a CFT 4-point functions of scalar phi, it looks like this. There's some overall prefactor and a function of u and v, where u and v are the conformally invariant cross ratios. And then the idea explained in these papers is to go to Mellin space. So instead of having g as a function of u and v, we do a Mellin transform, and we get a function of s and t, which is this m over here. The relation between g and m is a little complicated, but it's a formula one can use. And then the idea is that from the large s and t limit of this Mellin amplitude, one can extract the scattering amplitude in flat space. Okay. These Mellin space variables are denoted by st and u because they're related to the Mandelstam invariance and flat space scattering. So let me first explain through the 3D, 11D case, and then I'll talk about 4D and 10D. So in particular, how does this? What is this relation? Well, this is the relation. This is the scattering amplitude in flat space is related to that function m in this way. So we evaluate m at these values. So s and t now are the Mandelstam invariants in the flat space scattering process. So we evaluate m at these values, and then we do this alpha integral, and then we get.
So n was the Mellin transform of the 4-point function.
Correct.
And then you have to do some alpha integral.
Have to do some alpha integral, and then you have to take the limit L goes to infinity, where L is the radius of ADS, so that you get flat space.
This gives an exact answer, or just largest.
Yes.
In the previous slide you said largest, large t.
It is large S, large T, because the only thing that's going to contribute is, see L appears in here, so if I take L to infinity as just the leading power in S and T, that's going to contribute. So we expect m of S and T to have a series expansion in 1 over n, or in L Planck over the radius of ADS. And at each order in this expansion, it's only the large S and T behavior of this Mellin amplitude that contributes to the scattering amplitude, as I said before. But in order for this scattering amplitude to have an expansion in L Planck times the momentum, it must be that the Mellin amplitude, the expansion of the Mellin amplitude in L Planck over L takes a form like this, where at each order in the L Planck over L expansion, the Mellin amplitude is a function that doesn't grow faster than the kth power of st and u. So the growth of the Mellin amplitude at some order in the expansion is determined by what the scattering amplitude is at that order, and that is a constraint. Is this sort of clear?
I didn't understand this, that it should be a function, it should grow at k power.
You need A of S and T to have an expansion in L Planck times momentum. So say it's some order, it's L Planck to the 10th times S to the 5. Okay? And you know that only the leading term from here must contribute to that. So you need it to be such that that order in L Planck over L, so L Planck over L to the 10th power, it must be that all the L's cancel and we're just left with L Planck to the 10th times S to the 5 after you do this integral. So that determines the growth of this function, of that order. The growth gets worse as you go, the farther you go in the expansion.
So kind of a derivative expansion from the flat space point.
It is a derivative expansion from the flat space point of view. Yeah.
And if this were not to happen, suppose it were to be violated,
Yeah.
is there some sort of picture of that? Is there some sort of IR divergence or something? I'm sorry, it's a vague question.
Yeah, I don't know if that were not to happen, what would
Just dimensionally, if there is a flat space limit, it has to happen.
this has to happen. Yeah. So I'm going to impose this as a requirement.
Right. So somehow it would mean that the box is never unimportant. That's why I was saying
For instance,
You can't take the L going.
L goes to infinity limit. Yep.
L going to infinity is a singular limit.
yeah. So you get anomalous powers for the size of the box.
Yeah, instead of 1 over n or L Planck over the radius of ADS, I will use 1 over CT, where CT is the coefficient in the 2-point function of the stress energy tensor. It can be calculated. I'll show the formula for CT later. It can be related to n. You can either think of n or you can think of CT. CT goes like n to the 3/2, large n.
Sorry, I have one more question that's
Yeah.
tangential to what you're saying, but anyway. There are specific limits of the correlation function where the relationship between the amplitude and the correlation function becomes sort of simpler than this, right? In this Regge kind of scattering limit.
Yes, yes.
That's easy to see from this formula. This looks like a sort of complicated relationship to me.
Oh, right. It looks complicated to me as well. I'm not really sure. Okay. So to obtain the scattering amplitudes of the gravitons and superpartners in M theory, all we have to do, as given that formula, all we have to do is to compute the 4-point function of operators in the stress tensor multiplet in ABJM theory. So what are the operators in the stress tensor multiplet of ABJM theory? Well, ABJM theory is an n=8 superconformal field theory, has R symmetry SO8, and these are the conformal primaries in the stress tensor multiplet. The stress tensor over here has dimension 3 and spin 2, and then there are other operators. This is a supercurrent, the R symmetry current, and a couple of scalars. Because it's easier to think about CFT 4-point functions of scalars than operators with spin, I'll just focus on the scalars. What kind of scalars are there? There are 35 scalars of dimension 1 and 35 scalars of dimension 2, pseudoscalars. They transform in 35-dimensional representations of SO8, but they're different 35-dimensional representations of SO8. Okay?
They're related by triality.
The two representations, yes. And they're, yeah, right. And the task is then to find the Mellin amplitudes corresponding to the 4-point functions of these scalars. The Mellin amplitudes for a 4-point function of 4 scalars, or we can have 2 S's and 2 P's, or we can have 4 P's. Okay? So once we find these Mellin amplitudes, we can take the flat space limit using the formula in the previous slide and get the scattering amplitude.
So at the beginning you said that if,
Yeah.
or I thought you said that if you knew the dimension 1 scatterings that determined the whole multiplet.
Yeah, so why would you want to do, or why would you not just want to
Yeah.
focus on this one? You could. I'm mentioning these other two because they'll become very important in a bit. But you're absolutely right. However, keeping in mind that they'll become important in a bit, we can understand them.
You don't have to, but you can.
Yeah.
Yes.
Right. Yeah. You don't have to right. So this SSSS has some overall prefactor, and then there's 6 functions of U and V because of the R symmetry indices. There's 6 ways of forming a singlet out of 4 copies of the 35C representation. In SSPP, there are 3 functions of U and V. In PPPP, there's 6 functions of U and V. All of these are related by supersymmetry. The functions appearing in SSSS obey some differential relations that come from the word identities. So for example, these are some of them. One can also figure out how these other functions in SSPP and the ones in PPPP are related to the functions in SSSS. By figuring out what the supersymmetry word identities are, it's a very, in my experience, this was a very hard exercise to do, but we have some good Mathematica code that does it. So for instance, one of the functions in here is related to the functions in there by some differential operator. So we have all these relations. But he's right. Shiraz is right. In order to learn about flat space scattering, it would have been enough to just look at SSSS.
I'm sorry. You have different differential. No, it's the same differential. The fact that you have these 6 different structures, all of them obey the same word identity relations.
Sorry, 6 different functions. You're asking about the S's, or you're asking?
Yes, the SIs.
They're different. You can get them using crossing symmetry. You can get the other ones using crossing symmetry. So here I'm just relating SA S4 to S2 and S3. But I didn't tell you what S1, S2, S3, S4, S5, S6 are. So this is just to give you an idea of what the relations might look like. Yeah. Okay, so in general, computing these Mellin amplitudes is hard. But the point is, what makes this possible is that the contribution from tree-level Witten diagrams.
I'm sorry, and the word identities are for superconformal invariants.
Correct.
Yeah, so conformal invariants, all of them would just obey the same thing.
Conformal invariance just says this.
Just as this, right? The functions of scattering.
Yeah, they're functions of U and V.
Thank you.
Okay, so the point is that there is a set of requirements that can be used to determine tree-level, the contributions to the Mellin amplitudes from tree-level Witten diagrams up to only a few constants. And the requirements are the following. The Mellin amplitudes should obey the supersymmetric word identities. The Mellin amplitude should be consistent with crossing symmetry. At a certain order in the 1/CT expansion, the Mellin amplitude should grow as most as the nth power of ST and U. This comes from the relation between flat space scattering and the Mellin amplitudes. And the last one is that the Mellin amplitudes must have the right analytic properties that are appropriate for tree-level Witten diagrams. Meaning that they can have only some set of poles, or they can be analytic.
Why can you separate now between tree level, loop level?
Oh, I'm just, if I could separate between tree level and loop level, this is what the tree level would obey. But I know that the first few orders I can separate between tree level and loop level. Loop level comes with certain powers of 1/CT, and tree level comes also with certain powers of 1/CT, and the first few orders there's no overlap. So those are the orders that I'm going to be focusing on.
Is there a quick way to see that?
So just repeat the question to see.
To see the separation between the tree level and the loops.
So it
Small powers of 1/CT.
it comes from. It's the same question as this question over here. You know, the loop amplitude is over here. This is for scattering amplitudes, but for Mellin amplitudes, it's the same thing.
This is using supersymmetry quite heavily, right?
Yes, yes.
It's just like 9-dimensional analysis would give you much lower power for the loops.
Right. Okay.
Maybe a sort of more remedial, just diagram
Yes.
and the loops in it.
Correct.
Okay, and then, so your strategy to extract from the Mellin amplitude, the Witten diagram is just to look at, I don't know, the pole structure, or how are you, when you say the Mellin amplitude must have the right analytic properties?
Yes.
So if it encodes in it the loops and so on, then, you know, they will have, besides
We-
poles, other things.
Yeah, that's right. They
Is it
would have
meaningful that
more
part
poles.
away, is it?
So I'm not considering the contribution from loops. I'm just looking at contributions from, you know, contact diagrams and tree level exchange. And those it has been worked out how those contribute to the Mellin amplitude.
Mellin.
Yeah.
Okay, and then what you're going to do, if I understand,
Yes.
and then to keep the tree level, so is the whole thing,
Yeah.
so when you say tree level diagrams, you mean both including the possibility of tree level exchange in the bulk and contact diagrams?
Correct. Yes. Yes. Absolutely.
So you just take the Mellin amplitude which has been worked out, which only includes these, and use that, is it? Or you have to do something more? I didn't quite understand the last statement there.
So these constraints are that the Mellin amplitude can have so how do tree level Witten diagrams contribute to the Mellin amplitude? There can be poles in STNU with the residues given as being equal to the residues, the same residues that you get when you expand certain conformal blocks when you express them in Mellin space. Or they can just be, or the Mellin amplitudes can be just analytic, coming from contact diagrams. So that's all that can happen. So I'm just going to assume that's the case.
And this is true up to L to the power 9.
Correct. Even for the next power of L Planck, there's like for the next power after L Planck to the 9th, there was also just a tree level amplitude that contributes, because the next amplitude would be the L Planck to the whatever.
The next loop contribution.
Yeah, sorry, the next loop. That's right. So for the first few powers, there's no overlap. It's true. Eventually, there will be overlap, and you won't be able to separate out the loops from tree level. So then one would have to understand the analytic properties of the loop Mellin amplitudes.
To the order you work,
That's not the case. Yes.
Okay, in addition to, so when you say exchange diagram, you just have the exchange of the same multiplet, right?
Yes.
But if you were to consider massive particles,
Yes.
that also would mix with the loop contribution and so on, right?
That's right. But we don't know any.
That also has a separation, clear separation. Does it?
You
No.
know, massive particles at scale n Planck,
Yeah.
they will have, you know, decays of order, they decay in time of order Planck scale.
But when it considers loops, one has to take that into account.
There are no massive particles that we know of.
That will all get mixed up in the loop.
That's what I'm saying. So,
Yeah.
so that can be isolated.
You won't be able to distinguish that from. It's just all one piece.
Right.
You need a parameter to make them stable.
Okay. So how many? So using these requirements, how many solutions do we have? The number of solutions depends on the order in the expansion that in 1/CT that we go to, because at at higher orders, more Mellin amplitudes are allowed by this growth condition. So if we want the number of solutions of,
I missed that. Could you just say that last part? What is this order of Mellin amplitude?
sorry,
Oh,
so,
it's just
so at
order-
some order in the 1/CT expansion, we know the growth of the Mellin amplitude. It shouldn't be faster than some power of STU.
And then you're counting how many coefficients there are at that point.
And up to that order, I'm counting how many coefficients there are that obey all these conditions.
Right. Yeah.
And up to first order, there's just one parameter. For up to 4 orders, there's 2. Order 6, there's 3. Up to order 7, there's 4, and so on.
And is there some symmetry in this STU? Oh, you know, that
Yes,
is complete
crossing symmetry.
So that's why the powers are growing so slowly.
Correct. Right.
Sorry, can I think of this question that you're asking from constructing the CFT data beta from the scattering. Does it have to do? So can you go back to the previous slide? Does
Yes.
it have to do with the it's at most as nth power you say?
Yes.
But there are less powers.
Correct.
So that all becomes invisible. In
Correct.
the limit, right?
Yes.
So the job is to construct those values.
Correct.
And think of that as what is being determined.
Yes.
Okay.
Yes.
Because the
Yeah,
nth
the
power
Mellin
is
amplitudes,
amplitude,
the
right?
Mellin amplitudes differ from the flat space scattering amplitudes in that they have lower powers of STU as well.
So in the
That's
flat
at a
space
certain
limit,
order.
A bunch of things are forgotten, but you want to
Correct.
reconstruct it back.
Correct. Yes. Okay. So the number of solutions matches the number of solutions for the word identities for flat space scattering amplitudes. In order to determine what the Mellin amplitude is up to a given order, we have to compute these coefficients. So to determine m up to order 1 over CT, we should compute one CFT quantity, and if we compute that CFT quantity, we can determine this coefficient, and we can fix the Mellin amplitude. To determine the Mellin amplitude up to order 1 over CT to the 5/3, we should compute 2 CFT quantities, and so on. So how many CFT quantities can we compute? Well, we can compute 3 CFT quantities. I'll explain what they are. One of them being CT as a function of n. And then we can relate them to the Mellin amplitudes. So we can compute the tree-level Mellin amplitudes up to this order, 1 over CT to the 19/9. And therefore, we'll be able to reproduce the contribution of the R to the 4 term to flat space scattering, and also show that the D to the 4, R to the 4 doesn't contribute.
From the point of view of the bulk, these were all half BPS terms, or some BPS terms of the.
Yeah, certain various degrees of BPSness, yes.
And from the point of view of the boundary, they also they exchange supersymmetric double traces. They call it what, supersymmetric double trace exchange.
It's not just supersymmetric double trace exchange. You can get some non-BPS information from the Mellin amplitudes, yes.
So completely protected stuff in the bulk determines unprotected stuff.
Yes, it seems so.
That's incredible.
Yeah. And I'll show you an example of that, some anomalous dimension that I'll compute.
So the counting one is, you say that the number of solutions here matches the number of solutions for flat space.
Yeah.
But as we said, there is some things that we are forgetting, right, when you go to flat space.
Oh, sorry, I'm just saying. You're right. So if you look at up to this order, when I say 3, in flat space scattering, there's like 3 solutions up to that order and lower.
But at that order, there's one.
Only one, correct.
One is to be, we want to get 3 data.
Correct,
pieces of
correct,
things
correct.
from one.
Yes, yes.
Or less.
Okay, so what CFT quantities can we compute with supersymmetric localization? People computed, okay, so ABJM theory is a conformal field theory. We can study it in flat space, or we can study it on any other conformally flat space. People put it on the sphere, and were able to use supersymmetric localization to compute its sphere partition function. There's some mass deformations of this theory, and that have also been analyzed, and people were able to compute the S3 partition function as a function of these masses using supersymmetric localization. I'll show you the formula in the next slide. So that's a quantity that is computable. Sphere partition function is a function of the masses. How? Right, so using supersymmetric localization, one can write this partition function as a finite dimensional integral. And then one can use some statistical physics techniques to extract the free energy, which is minus the log of the partition function, to all orders in the 1 over n expansion. So these are quantities that are known to all the orders in 1 over n. As I'll explain, the following quantities can be related to SSSS, SSPP, and PPPP. and they can be used to determine the Mellin amplitudes up to this order. So these are the three CFT quantities that we can compute. One of them is the second derivative of the free energy with respect to one of the masses, evaluated when the masses are 0. And the other two are fourth derivatives, either with respect to one of the mass parameters or a mixed derivative. Just to show you what the formulas look like. So this is the S3 partition function as a function of the two masses. It's just a 2n dimensional integral. It's got some sinh and coshes, and the mass parameters appear in the denominator. At finite n, one can evaluate this integral exactly.
This is for ABJM at k equals 1?
This is the ABJM for arbitrary k. K appears here, but you can set k equals 1. And at large n, one can rewrite this partition function. It's not obvious, but one can do it. To rewrite it as a partition function of some non-interacting Fermi gas of n particles. The particles have a funny kinetic energy, not p squared. It's a more complicated function of p, and they move in a funny potential, and the potential looks like this. And one can use statistical physics techniques to figure out what the partition function is. Then the partition function takes the form of some area function, where the argument is some function of the two masses times n, shifted by some other function of the masses. These functions are pretty simple. You can find them in our paper or in other papers. One nice thing about it is that at large n, one can show, given this formula, that the logarithm of the partition function goes like n to the 3/2, as expected from 11D superconducting. Okay?
Sorry, so just to understand, I mean, is the point, this might be remedial, that the 4-point of function of SSSS, the kinematic dependence, etc., is all completely known, only the coefficient has to be fixed, and that you fix by taking two derivatives of the free energy.
The kinematic is known given that one imposes, so the position dependence is known given that one imposes these conditions. So when I say here that you have some number of solutions, yeah, we know what those solutions are as a function of the x's, and there's just some numbers that need to be determined. Yes, that's right. And the numbers will be related to these derivatives of the S3 free energy as of with respect to the masses. That was our idea.
Like you said, 3 CFT data points.
1, 2, 3.
But sorry, the counting was 1 plus 2 plus 3.
Oh, sorry. These things are known to all orders in the 1 over n expansion. So to all orders in the 1 over CT expansion.
No, I mean in the previous slide.
Yes.
Okay, here itself, you said the last line, there are 3 things that are.
Yeah, so at a given order in the 1 over CT expansion, I need to determine 3 things. So those 3 things are this, this, and that expanded to that order in the 1 over CT expansion. Okay. So then the question is how to relate these derivatives of the free mass deformed free energy to SSSS, SSPP, and PPPP. And here it's going to be important that we have these other ones as well. First, I'll do the second derivative, then I'll do the fourth derivatives, because those are harder. Well, first I'm going to explain roughly how it goes. So what do these mass deformations look like? In the Lagrangian, we have some mass parameter, and the mass parameter multiplies some operator that's integrated over the whole sphere.
Sorry,
Yes.
one remedial question as well. You said you have these conditions on the Mellin space amplitude, and
Yes.
that determines the structure of the amplitude
Yeah.
up to some ambiguity. Is the spirit of this determination something like it's an analytic function? I know its poles, I know its behavior at infinity, and that determines it up to a few numbers.
Yes. Okay. Mass parameter multiply some operator. On the sphere, it's a linear combination, linear order in M. There's a linear combination of a dimension 1 operator and a dimension 2 operator. the dimension 1 operator is a linear combination of the 35 scalars S, and the dimension 2 operator is a linear combination of the 35 pseudoscalars P. If we take two derivatives with respect to the mass, we get the integrated two-point function of this operator. If we take four derivatives with respect to the mass, we get integrated four-point function of this operator. We know that J's and K's are related to the S's and the P's by group theory, so we know that relation. So we just have to plug it in and evaluate these integrals.
So at large n, it seems that you got the functions of m1 and m2 exactly anyway.
Yeah.
So you could take any number of derivatives that you want.
Yes, that's right, and those would give more than four, integrated endpoint functions where n is bigger than 4. Those I wouldn't know how to relate them to the 4-point correlator. Okay. So first, let me explain how the 2-point function is related to the 4-point correlator, and then I'll so first this integrated 2-point function, and then how this integrated 4-point function is related to the 4-point correlator. The integrated 2-point function. So because S and P belong to the same multiplet of the stress tensor, and the 2-point function of the stress tensor is proportional to CT, that means that the 2-point function of S and 2-point function of P is also proportional to CT. Because the J's and the K's are linear combinations of the S's and the P's, that means that their 2-point functions are also proportional to CT. So what that means is that this integrated 2-point function over here is proportional to CT. This is a relation. If you work out the numerical factor, it's given by this. So this is the way to compute CT in this theory. It's just the proportional to the two derivative of F with respect to the masses.
Does that come as a zeta function?
Some multiple of zeta 2?
This is zeta of 2, but I don't think it's related to the other zetas that appeared in string theory formulas. Or I don't know what's related to what. Okay, how is this related to the 4-point function? Well, there's a 4-point function has a conformal block decomposition. So there's overall prefactor and then sum over conformal blocks with coefficients, OP coefficient squared. In a normalization where the identity appears with coefficient 1, then the OP coefficient with which the stress tensor multiplet appears is inversely proportional to CT. This is the relation. So given the formula for the Mellin amplitudes that we had before, in terms of those undetermined coefficients, we can decompose it in superconformal blocks, and then we can look at the coefficient of the stress tensor and set that equal to 1 to this expression. So this is how we determine one coefficient.
This is basically the same statement that the 3-point function is purely Einstein. Meaning, if you know the coefficient of the Einstein action,
Yeah.
that completely determines graviton exchange.
Yes.
Because it was all coming from the Einstein.
Yes. Yeah.
And CT is determining Newton's constant.
Right. Yeah. So essentially, what's going to happen is that it's only CT is only going to appear. So the stress tensor. That OP coefficient, stress tensor OP coefficient, only receives contributions from this solution over here.
Yeah, I mean, in just a non-supersymmetric theory, you would have had a 3x3 block of stress tensor exchanges. And you would have had to specify, in order to specify this part, you would have to specify lots more data. But here, because the 3-point function is very simple, it's just one number. It's completely Newton.
Right.
You must go on, but I mean the 3-point function SST is fixed by general coherence, right?
No, but what he meant was that in TTT that
in
would be
TTT
kissed.
answer, but here
It's all mixed up because they're all compensated.
In this case, they're related. SST is related to TTT. Yes.
Sure.
You're right.
Yeah. But in SST, it's correct. You don't have to worry about the 3 structures. Okay, so now that we know what CT is in terms of n, and we know what these other things are in terms of n, I can show you some formulas. So this is the fourth derivative of with respect to m1, and this is the mixed derivative, and now I'm expanding them in terms of 1 over CT because I determined what CT was in terms of n. So the expansion looks sort of like this. If you want to get a feel.
Your comment says there's no R cube term
Yeah.
in supersurface.
Yeah, it's all to me. It's all
Yeah.
Fine, fine.
Yeah,
I got it. Okay.
Okay, so then we should just impose these, well, we should just impose the constraint that these four derivatives expanding in 1 over Ct as such is equal to this integrated 4-point function. Now, how do we compute integrated 4-point functions? That seems hard. So here's the general field theory result about integrated 4-point functions. So if I have two operators, A and B, and the 4-point function looks like this overall power of the x's and the function of u and v in flat space. Then when we study the CFT on the sphere, the 4-point function just gets modified by the conformal factor. And then the integrated 4-point function takes this form. So there are various powers of the conformal factor that appear. So in order to go from flat space to the sphere, the conformal factor is just 1 plus x squared over 4r squared, and there are various powers of this that appear in here. And what we showed is that even though this has 12 integrals because it's an integrated 4-point function, we can reduce it to 2 integrals using various symmetries. So we can reduce it to an integral over u and v of this function g of u and v that appears here, multiplied by something. What that something is actually sort of interesting. It's actually a contact Witten diagram for a 4-point function of operators of dimensions 3 minus delta A and 3 minus delta B. It's not obvious why Witten diagrams appear here, because this is just a purely CFT calculation. I'm just studying the integrated CFT 4-point function. So these d bar functions, this d bar function that appears here is, so the contact Witten diagram is given in terms of some d function, and the d function up to some overall coefficient is related to the d bar function. Yeah.
So see, here the GUV, the 4-point function, that would be fixed in terms of value.
Correct. Yeah, that's right. So I have the Malin amplitude with some undetermined coefficients, and then I just plug it in here, and I get some expression on the right-hand side. I get some expression in terms of those undetermined coefficients, and then I just set it equal to whatever it was over here. Okay, so that's the strategy. So summary. So superconformal word identity, asymptotic growth in Malin space, and crossing symmetry in the analytic structure of the Malin tree amplitudes determine the Malin amplitudes for SSSS, SSPP, PPPP, in the 1 over CT expansion up to a few undetermined constants at each order. With supersymmetric localization, we can compute the S3 partition function as a function of the masses, extract the free energy in the 1 over CT expansion, and then evaluate the second and fourth derivatives of the free energy with respect to respect to the masses, and those give conditions on the integrated correlators, SSSS, SSPP, and PPVP. And if we combine everything, we can determine what MSSS is, SSPP, PPPP, up to order 1 over CT to the 19/9. And then we can take the flat space limit and determine scattering amplitudes in 11.
CT to the power 19. Is that LP to the power 19?
No.
LP to the 19. Sorry, just what is that LP?
19/9 appears here. Let me try to see. It differs from this one by, so 19/9 minus, it's 10 by 9. And that's just because it's got 10 more derivatives.
Yeah, LP.
Yeah.
Okay.
Because it's d to the 4r to the 4. Yeah.
Yeah, maybe I didn't. I wanted to understand this weird fractional powers of 1 over CT.
Oh, okay.
So
Yeah.
I thought that CT was like 1 over CT was like Newton constant.
Correct.
Now, if I do flat space quadration theory, then G mu nu is equal to eta mu nu plus square root of Newton constant times h mu d. So in all my vertices, it will appear like that, and
Yeah.
all the propagators will be conventionally normalized, so there will be no.
Yeah, so you'll just have integer powers.
So yeah, so I thought that I can only get integer powers of square root g.
Yeah, unless, yeah, so if you just have supergravity, that's correct.
Okay.
But you could have other interaction vertices, like an interaction vertex that's r to the fourth,
All right.
and that must come with an extra power of L Planck in order to account for the fact that this has 6 more derivatives than that one.
But L Planck would also be that power would also be some integer power of the
No,
Newton constant.
No, because the Newton constant goes like L Planck to the ninth,
Oh yeah, okay.
because it's 11 dimensions. So that's where the fractional
Yeah,
powers
yeah,
appear.
yeah.
That's where the 9 appears.
All right. Guys.
Silviu, what happened to the UV divergences when you
There are no UV divergences in this computation.
but if you have integrated, you have 4-point function, clearly there is a divergence corresponding to the
Not in 3 dimensions, and not for these dimensions of the operators. I'm looking at the connected 4-point function.
So no identities,
No identities.
and all others are higher.
Yes. Yeah.
I mean, the
So
operator dimensions are high, so
yeah. So in 3 dimensions for these particular values, there's no
sorry, in the SSOP there is S, there is probably S in the SSOP,
yes.
so that is a divergence.
Yeah, but it's not big enough. When you integrate it, it's integrable. Okay. Okay, so I said this. Now the flat space limit. The formulas, unfortunately, the formulas for these things are very complicated. So, but you can find them in the paper. The flat space limit. Then you take the flat space limit, and it implies you reproduce this fr to the fourth, and you can show that fd to the 4r to the 4 is 0.
Could I ask the converse question too?
Yeah.
I mean, if there's no UV divergence, does that mean there must be an IR divergence for the same challenge?
Yeah, in flat space, but these are integrated 4-point functions on the sphere.
Ah,
That's where the sphere was important.
okay.
Okay, so the fact that we reproduce these things is a precision test of ADS-CFT beyond supergravity. To go beyond fd to the 4r to the 4, one has to compute more CFT quantities. But if we're interested in the CFT correlator at, so what we can do is, use the extra piece of information that we know. We know what fd to the 6 r to the 4 is, we can use that as input to determine the CFT correlator at the next order, at 1 over CT to the 7/3. So we can just use this as input. And then once you have that CFT correlator, you can extract anything you want from it, any piece of CFT data that you want. So this is an example. This is an example of that. We can extract the dimension of the lowest unprotected operator up to order 1 over CT to the 7/3. And it sort of looks like this.
Now just to understand roughly what's going on. I mean, even if we had just Einstein gravity, that leads to some anomalous dimensions for double traces, which is basically Newton's law using the protected Einstein information. So this is the analog of that trace. So you found some bulk terms,
Yes,
and now you can find therefore the interaction energy between two particles
Correct.
using those bulk terms.
yes, yes,
You're reading off that.
yes, yes.
Thank you. And it's just tree level exchange of that. I mean, there's no.
Yeah, it's all tree level.
Yeah.
There's some coefficient here, say 1 over CT squared, that will come from supergravity 1 loop. But that one I don't know how to determine.
Right. So your point is that even if there are protected terms in a Lagrangian, we have that Lagrangian, then of course we can do non-protected physics.
Correct.
By the way, if you supplement this logic with the inversion formula, then could one imagine that without the CFT input, just from the flat space scattering, let's say, the CFT amplitude would be fixed
It's not fixed.
because of this?
This was done in the 4D example, but it's not fixed.
Could you say it in what you meant?
Yeah, so
I'm sorry.
here,
Yeah.
so here which are lower powers,
Yeah.
right? Which the you use the CFT quantities to determine those. But at the end of the day, they, as Shiraz has been saying, give rise to some double trace exchange with spin supported up to a certain
Yes.
value given by the contact terms.
Yeah.
Now, usually the consequence of the inversion formula is that to a given correlator, the ambiguity is only supported at a very small spin, one. But when it's supersymmetry, that one can even be taken down to zero. So there is no ambiguity. So in that sense, there is some notion of uniqueness that had to be the case, that this had to be the solution. The inversion formula can be thought of as constraint of contact terms.
Yeah, consequences of the inversion formulas were studied in the 4D case, but there it didn't determine completely.
Yeah, but if you were to do that, do you conceive that such a thing?
It would
There's a
could
possibility of
impose some constraints, yes. But you'd have to look at slightly more general correlators, not 2-2-2-2. Not the SSSS. You have to look at the other half BPS operators. Okay, good.
Sorry, just one. Let me
Yes.
have to understand the 1 over CT square. So you say 1
Yeah.
over CT square can only appear from loops,
Gravity.
and not from some tree-level higher derivative object.
Yes, that's right.
Why? I mean, how can one see that?
Because this is the difference. So if it were a contact term, it would have to have 9 more derivatives than the Einstein-Hilbert term. But we can only write down contact diagrams with even number of derivatives because they're written in terms of R. Okay. I have 2 slides that are just tangent, which is that to go beyond d to the 6th r to the 4th, then maybe one can apply a similar philosophy, but their supersymmetric localization wouldn't be enough. But maybe numerical conformal bootstrap could help. And as evidence for that, well, first I should say that there's some other OBE coefficient in the superconformal block expansion of SSSS that can also be related to the 4th derivative with respect to the mass. I might explain this tomorrow. But given this fact, we can compute this OBE coefficient in various known theories, and we can plot it as a function of 1 over 16 over CT in this case, and it looks like these dashed lines. So there are some n=8 theories with supergravity duals and some n=8 theories without supergravity duals. The one with supergravity duals, for them CT goes to infinity. There's a limit in which the CT goes to infinity. CT goes like n to the 3/2 of large n. This is the region over here in the plot. And for the theories without the supergravity dual, then CT, this OBE coefficient is over here. So they don't approach this regime. Now, for a theory with n=8, for an n=8 superconformal field theory, one can get bounds on these OBE coefficients using conformal bootstrap. The allowed region is this region over here, the shaded region. And you can see from this plot that the known values of this OBE coefficient come very close to saturating the lower bound given by the conformal bootstrap. The fact that the lower bound is saturated, so if we conjecture that the lower bound is saturated, then the solution to crossing symmetry should be unique.
Which OP coefficient?
Of some quarter BPS operator.
Okay.
Yeah.
So that's a double trace?
It is a double trace, yes. So if we conjecture that the conformal bootstrap bounds are saturated, then one can extract the solution to crossing from the numerics, and from that one can extract any piece of CFT data that you want. So for instance, some unprotected scaling dimensions, they look like this as a function of 1 over CT. And if this is done to a high enough precision, and if this is correct, then this can be used as extra input. And one can maybe reconstruct more of the 11D effective action.
These are all double trace operators?
These are all double, these are all double trace operators. Yes.
So they're going to something simple at large C.
Yeah, large C is over here. Yeah, 2, 4, 6, and so on. Yeah, the scalar, the external scalar has dimension 1, so 1 plus 1 is 2. So now if you have two derivatives for spin 2, it's 4, and so on. Okay. I mean, I was going to also talk about n equal 4 superhang mills, but I don't want to keep you guys.
Well, we could do another 20 minutes if you could.
Okay, 20 minutes sounds good? Okay.
If you'd like a 2-minute tea break, you should.
No. Okay, this is going to be faster because it's similar in some ways. Okay, so now to obtain scattering amplitudes of gravitons as superpartners in type 2B string theory, we can look at the stress tensor multiplet at 4D n equal 4 superhang mills. The 4D n equal 4 superhang mills theory is an n equal 4 superconformal field theory. It has R symmetry SO6. The operators in the same multiplet as the stress tensor, there's a list of operators. In this case, so there's the stress tensor over here, and then there are 3 scalars in this case. There's dimension 2 scalars in the 20 prime representation of SO6. There are dimension 3 scalars in the representation 10 and 10 bar of SO6, and also complex dimension 4 scalar. Okay. So now, if we want to study these 4-point functions, SSSS, SSPP bar, and so on, in this case, we have 2 parameters. We have n and lambda. So we should consider a double expansion in 1 over n and 1 over lambda. Or equivalently in 1 over ct and 1 over lambda. In this case, ct is known to be n squared minus 1 over 4. Okay? And to reproduce the tree-level scattering amplitude, we want to find the Melian amplitudes SSSS, SSPP, and so on at leading order in 1 over CT in the 1 over lambda expansion. And then the same requirements as before. The Melian amplitudes obeys the supersymmetric word identities. There's this crossing symmetry that at a certain order in the 1 over lambda expansion, the Melian amplitude grows at most as the nth power of ST and U. And then that they have the right analytic properties for T-level Witten diagrams. These determine these Melian amplitudes up to a few constants. And this is a similar table to the one I had before, where you see that at a given order in the 1 over lambda expansion, there's some number of parameters. And the number of parameters matches precisely the number of solutions, the word identity for flat space scattering amplitudes in the same way as before. So in this case, in order to determine the 4-point function up to some order, we just have to compute some number of quantities. How many quantities can we compute in this case? Well, I already told you that CT is n squared minus 1 over 4, so that's one quantity. In addition to this, we can compute one other quantity, and therefore determine what the 4-point function is up to this order. 1 over CT and 1 over lambda to the 3 halves. And this corresponds to the R to the 4th term. What quantity can we compute in this case? Well, it's similar as before. N equal 4 superhang mills was studied on the 4th sphere in the presence of a mass deformation. So one can compute a mass deformed partition function. In this case, it's more complicated. It's given by some integral like this, and this function h is pretty complicated. But it can be computed at leading order in 1 over n. In the 1 over lambda expansion, this thing, the free energy can be computed, and it sort of looks like this. So you see some zeta functions appearing. These are the same as the zeta functions in the flat space scattering amplitudes. Okay. And now, as before, m, the mass, couples to, sorry, so maybe I should emphasize that, so before we computed the four derivative respect to the masses. Now the quantity that we have been able to compute is this mixed derivative, where we take two derivatives with respect to the masses and two derivatives with respect to the coupling, to the complexified coupling, or two derivatives with respect to lambda. Computing four derivatives with respect to the mass seems a little hard, but maybe it can be done. Okay, and so what do I want to say? So the mass couples to this integrated operator over the sphere. And we also took two derivatives with respect to the coupling, so we should ask what the coupling, how the coupling appears in the Lagrangian. It multiplies some integrated operator, but this is a dimension 4 operator. So this mixed derivative, two derivatives with respect to the masses, two derivatives with respect to the coupling, gives an integrated 4-point function where two of the integrated operators are this ij plus k that correspond to the masses, and two of them are marginal operators. It can be shown that the integrated marginal operators, dimension 4 operators, can be replaced in a supersymmetric, so in the supersymmetry preserving case, they can be replaced with insertions of the north pole and the south pole of the sphere of some other operators. Okay, that I call J prime. So if we think about the n equal 4 Lagrangian as having in n equal 1 language where we have three adjoint chiral multiplets with scalars phi I and fermions chi I, then these J's are trace of the phi's squared and k is trace of chi squared, and this J here is also trace phi squared. Anyway, so it's the same idea as before. One can use this integrated 4-point function as a constraint. And then one can determine the Mellin amplitude corresponding to SSSS at order 1 over CT, expanded in 1 over lambda, up to order 1 over lambda to the 3/2. And then taking the flat space limit, one can find this expression, which is the scattering amplitude in flat space up to that order. And this is a precision test of ADS5 CFT4 beyond supergravity because we reproduced the R to the 4 term. To go further, to learn about the CFT correlators of the next order, one can use the scattering, what we know about the scattering amplitude at d to the 4, R to the 4 order as input. So to determine this at the next order, one need to know two quantities. One of them can be extracted from this derivative that I explained of the free energy, and the other one can be taken from the limit of the flat space scattering amplitude. And this is the answer for the SSSS Mellin amplitude. There's some part that's also appears in the free theory. There's some there's some operator, differential operator that also depends on the R symmetry indices, and then there's the rest. This is the supergravity contribution, this is the R to the 4 contribution, and this is the D to the 4, R to the 4. Given the 4-point function up to order 1 over lambda to the 5/2, one can again extract any piece of CFT data that we want. So for instance, the dimension of the lowest double trace operator in this case is given by this expression. So it starts at 4, and then there's at order 1 over n squared. There's an expansion in 1 over lambda, and we can extract the first three terms. Okay. One can generalize this analysis to higher BPS operators, not just the superconformal primary of the stress tensor multiplet. In n equal 4 supragonals, there's a tower of half BPS multiplets that are indexed by this P. They're roughly operators of the form trace phi to the P. And one can compute the S4 partition function in the presence of insertions of these operators at the north pole and the south pole of the sphere by some modification of Pashtun's localization formula. It's given by this. I don't want to bother you with the details. This is the result. Well, it also there's more that goes into this. We can discuss this. There's a conjecture of these people that's used. So this is the Mellin amplitude corresponding to SS, SP, SP. So SP, SP, SP is a superconformal primary of this of these other half BPS multiplets. Okay, so some complicated functions of P appear. And from this, one can also use the work of these people to extract anomalous dimensions at order 1 over n to the 4th. Okay. In conclusion, combination of techniques, supersymmetric localization, the word identities, Mellin space can be used to recover graviton scattering amplitude of small momentum in 11D and 10D from ABJM theory or from n equal 4 super Yang-Mills. In 11D, we can reproduce this f to the 4th and show that fd to the 4r to the 4 is 0 from ABJM theory. And in 10D, we can reproduce fr to the 4th is given by this expression from n equal 4 super Yang-Mills. We can, if we want to learn about the CFT, we can use supersymmetric localization and flat space limit to compute correlation functions in the CFT to one more order. And then for the future, we can hopefully one can think of generalizing this to other dimensions, other 4-point functions, higher point functions, less supersymmetry, and so on. Maybe one can learn about loops. This was all tree level. Maybe we can think about loops in ADS, and also I think numerical bootstrap could be useful to go further. Yeah, that's all. Thank you.
Yes. The R to the 4 term in 2B supergravity.
Yes.
That's the term that has this full instant-on sequence correction.
Yes.
So the analytic structures from the point of view. So suppose one were to focus just on the R to the 4 term.
Yes.
But restrict the condition that you were working at tree level.
Correct. Yeah.
Then it would appear that you have almost as much power as before.
Yes.
And you might hope to be able to reproduce the whole function.
Yes.
That would be it. Is that realistic?
Yes, I think so. What that would imply is that you could see, so there's some Eisenstein series as a function of G string.
Yeah.
The hope would be that maybe that's, that will appear from the S4 partition function.
Right.
But in order to see it, so in the S4 partition function, there's something you can ignore if you're just looking at the limit that I was looking at, the leading order in 1 over n. There's these instant-on corrections from the north pole and the south pole of the sphere. But those would have to be taken into account in order to reproduce this Eisenstein series, presumably. But yeah. So I think this line of thinking actually says something interesting about the S4 partition function. Yeah.
Right. Now the Eisenstein series was fixed by S duality. At least that was one way of
Yes.
of fixing it. And the instant partition function also has the S duality.
Yes.
Maybe. Well, okay.
So maybe there's a way to actually prove it
Yeah.
without actually computing it, but
Yeah,
just say that it must be that from general arguments.
Right.
Yeah. We considered thinking about a proof at some point, but it seemed complicated.
Okay.
Yeah. But yeah.
When you say the precision test of ADS CFT,
Sorry?
precision
Yeah.
test of ADS CFT beyond super. So the answers that you produce from CFT are matched with the Mellin amplitude, right? So this is a direct bulk calculation?
Well, the answers that you produce from CFT, you can convert them to the Mellin amplitudes, And then you can match them to the scattering, flat space scattering amplitudes. Yes. Yeah, I would think that reproducing vertices in, you know, effective action, I
But
think
there is
that would
more,
be.
there is more that you get, right, out of CFT.
That is more, but yes.
But those, is difficult to actually do the computation.
The subleading terms in the Mellin amplitudes, those that don't contribute to the flat space limit, I think it would be interesting to understand how to determine them, if it's possible to determine them at all, in some other way.
Berkowitz kind of, or strict field theories. Meaning it would be like an alpha prime correction that is. Oh wait.
No, I think it's a curvature correction. It's just the fact that it's not flat space, that it's the fact that it's
Just putting
curved
the string effective action onto ADS.
onto ADS. Yes, that's right.
Okay, so. Okay.
So it would have terms with the box regulator.
Yeah, that's right. That's right. Yeah, I think that's their interpretation. Yeah, that would be, once you reduce r to the 4 or whatever in 10D. Sorry, when you study the theory on the ADS 5 times S5 background, this generates some, I don't know, r squared with some extra powers of 1 over L.
Okay. That also makes clear that these are not independent data because they come from the same. It's the same flat space stuff, compactified in a new solution. Or is it getting contributions from other flat space things on this new solution?
Well, that's not clear to me. It could be some non-local things that would become local once you look at once you look around an ADS 5 times S5 background.
I see.
So I don't know to what extent they are determined, but I mean, yeah, I think it's an interesting question. I don't know what to answer.
One thing you could ask is if you just take these terms in flat space, the terms that you were able to determine,
Yes.
and then compactify on ADS using just those terms, do you reproduce the right lower terms?
Yeah, that would be the question.
And
The
you
answer.
suspect the answer is?
Oh, I don't know. But I think it's, I think that this calculation, while in principle it's presumably possible to do, in practice it's just, there's no way probably.
Yeah.
That would not be a better diagram. It would be a better diagram, right? Contact better diagram that you would have compared.
To do.
Those terms with what you are.
Yeah, that's right.
So
Yeah, I mean.
what is the issue? I mean, Witten diagrams, contact Witten diagrams are not.
Oh, no. The reason is that the supersymmetric completion of the r to the 4 term in 10D or 11D is not known. And you'd receive when you go.
You can just compute the Witten diagram of the graviton.
Would you
Yeah, but that's not enough.
to start with, would you have to correct the background solution also with these terms? I mean, for instance, with the symmetries make it ADS 5 times S5, but the radius of ADS could also receive contribution to these terms or not?
From what? From the higher derivative terms?
Yes.
Yeah, it could. Yeah, I don't see a reason why it shouldn't.
Yeah. Yeah.
Or the relation between the radius of ADS4 and the radius of S7 could change.
Yeah.
Maybe if the.
And also the absolute value, right? The absolute value.
And also the absolute value.
I have sort of technical question. In the mass going to zero limit, you said that this S4 partition function became a Hermitian matrix model with polynomial potential.
Oh, sorry. The one over. Yeah, this one is just a Hermitian matrix model in the mass goes to zero limit because these H's go away. Yeah.
So for non-zero mass, is there some? Is it like a matrix model with some fundamental something? I mean, I'm
It's
just
a-
wondering whether it's.
It's a with non-zero mass is non-Hermitian, so the interaction between the eigenvalues is not there's some complicated function of the difference of the eigenvalues.
So you're saying it's a complex what can I, is this something identifiable with the finite mass? I mean,
Well,
it's not a matrix model anymore.
I don't think it's well, I don't know what you call a matrix model, but
It's a random matrix integrally.
yeah, it doesn't. I mean, these are eigenvalues of matrices, but I don't know how to write down. Maybe it's possible to write down as an integral over matrices, even when the mass is in 0. Yeah, I'm not really sure, but yeah, the simplification when m equals 0 is that these h's go away, and there's just this factor. If you put this in the exponent, so it will be e to the log of this. So that means that the eigenvalues, there's a logarithmic potential between the eigenvalues.
That's there, even in the.
And that's the case in the Hermitian matrix model.
any cases,
Yeah,
even
that's
with
right. That's right. But with this h, it becomes much more complicated.
What equal is the function? What kind of function is h?
What kind of function is h?
It's a Gauss function.
I need to remember. I think it's more complicated than gamma. Not a, yeah. It's in Peston's paper.
I mean, it feels like if it were to be a matrix model, it would have to involve multi-traces. Because anything that involves just a single trace would be a function of just AIs. Right? It's like V of AI. The AI minus AJ could come if you had two traces.
Yeah,
There's
yeah.
A and an AI and an AJ.
Yeah, I don't think it would be, it may not be a matrix model with non-zero.
I mean, in the old days of matrix model, people also considered matrix plus vector fundamentally stuff. So this
Mhm.
mass deformation is of what kind of, these are some fundamentals, right? Or, no, sorry, what are these mass deformations are? Of things which are already present in the n equals 4.
Yeah. It's a mass for a hypermultiplet. Yeah, yeah.
Oh, okay.
Yeah, so we can think of it as an n equal 2 theory, as the vector multiplet and an adjoint hypermultiplet, and this is just a mass for the hypermultiplet. That's all there is. And it's adjoint.